let's start. The screen is visible.
Yes.
Okay. Earlier, where we were, okay, I was explaining this property, right? Okay, so it's basically like if f is a convex function, then it is bound to follow this property. Okay, so we are skipping the proof because we are not interested in proof. We will just apply it some machine learning stuff. Okay, if f is a convex and it is continuous and once differentiable at least, or you can say f belongs to c1. Okay, c1 is basically the set of all functions which is once differentiable at least and continuous. So if f is convex and it belongs to c1l, then c1, then it follows this particular property that f of y will be greater than or equal to f of x plus gradient of fx y minus x. Okay, for all yx belongs to domain of f. It's basically the domain of f. Okay. um Second property is okay, so why the convex functions are nice. Okay, so basically why convex function are nice. They are nice because every local minima is a global one. It means if f is a convex function, okay, and I found its minima, then it must be a global one. See, in machine learning, what happens? If you have a loss function lx, okay, so it's basically a loss function. Okay, so it's basically written as lx comma w. Okay, so in loss function, what happens in machine learning? You have to minimize the loss. Okay, with respect to this w. W is basically parameters. We will explain it later in more detail. But to give you a rough overview, and in machine learning or deep learning, this is a very highly non-convex function. It means it's the loss functions, mostly the loss functions, they are very bad in machine learning and deep learning in existing literature. Okay, so in 2D, let's say in 1D, they can be of any shape like this. So what happens when you tend to minimize this particular loss function? As you can see, this part is a global minima, right? But let's say if I start from here, descending, okay, so it's basically how you optimize the loss function. You use some what we say descent based methods. Okay, we won't go into the depth of descent based methods. It's basically, have you heard about gradient descent? Anyone?
Yes.
So gradient descent, what happens? You initialize, so it's a loss function. So this curve is a loss function. You initialize from somewhere and you tend to move towards the minima, okay? Or you tend to move towards where the slope is decreasing. So what happens in gradient descent algorithms, if you start from a point and you make your descent, okay, once you reach some kind of minima or some inflection point, you are not you won't be able to move upward. Okay, it basically doesn't moves upward, so it stucks in local minima. That's what we say. It stucks in local minima, and it's a very what you say, it's a very common problem in all machine learning or deep learning. Yet you start from some point, you make your descent, okay, in every step, and then you reach some local minima, you get stuck there. Okay, so basically the gradient descent stucks where the gradient of the function is zero. As you can see at these points, the gradient of the function is zero. So wherever it will find the gradient of the function is zero, it will get stuck there. Okay, so what happens? The optimal solution is supposed to be here, right? The optimal solution is supposed to be here, but the algorithm stucks in local minima, so it won't give a good what you say good image of the loss function as well as the good image of the parameters. Okay, so the function is not so yeah, it doesn't gives a good image about the machine learning model. It's not optimized well, and there is a possibility that it can give a high test error. Okay.
This genetic algorithm can be used, right?
Genetic algorithm, it's a totally different field. I haven't read about them, and basically in machine learning, as far as the optimization is concerned, I haven't personally read much paper on the genetic algorithms. I don't know, maybe their complexity is too high
Yeah,
or something.
because I
But
understand genetic algorithm can find out the global minima.
okay, yeah, and other things basically include that these loss functions are basically very high dimensional function. Okay, so so right now I'm working with a loss function in one of my project. So it basically, these kind of loss functions are, first thing, they are highly non-convex, and second thing, they are very high dimension in nature. The thing is, you cannot imagine the loss surface. This is a 1D representation of a loss surface, but in high dimension you don't know how the loss surface looks. Okay,
Right, right,
and
right, right. Yeah, you're yeah.
as of now, the loss function which I am working recently, it's something what it is, it's yeah, it's basically, it takes a tensor. It takes a tensor and gives a tensor. So you can see it's a very, very high dimensional loss functions. You cannot visualize it. Okay.
Correct, correct. Yeah.
So these are the problem. But the thing is, for convex function, you know that whatever is local minima, that's the global minima. It means if you get hold of a convex function as a loss function, so let's say if f is a loss function, okay, so it will be a nice loss function like this. In high dimension also, so it's basically when I say that in convex functions, every local minima is a global minima, then it's valid for high dimension also. Okay, so it's a very general statement. So even in high dimension, if you start with some point, you are eventually going to get converged to a global minima, and you will get a good solution. Okay, so this was the motivation, and we are going to prove it. Okay, so um, let's write the statement. Okay, if fx is a, can you please mute? There is a noise from your background. There is a, excuse me, there is a noise from background. Let me just. So if fx is a convex function, then we say every local minima every local minima is a global one. Okay, now we are going to prove this. Okay, so we will use this property. So you remember, this is the property that we first learned about convex functions, right? During the starting. So everyone remembers this property, right?
Yes.
Yes.
Okay, so we will be using this property. And now let's assume x star is a local minima. X star is a local minima in some delta neighborhood. So you guys know the difference between a global and a local minima, right? Or can I just go through it?
I think you can proceed, Alok.
Okay. Yeah. So if x star is local minima is basically like in a particular neighborhood, the function value at this particular point is supposed to be lesser than all the other points in a neighborhood. Okay. So it means that fx star is going to be less than or equal to f of y for all y belongs to the delta neighborhood of x star, right? So let's say that this is a function, this is a local minima, and this is a global minima. But if I can see here in this particular neighborhood, the function value is this point is less than equal to every other point. But if you go far from the neighborhood, like some this points, then the function value is then the function value is lesser than that of the local minima, right? So x star is a local minima in delta neighborhood. It means the value of fx star will be less than or equal to f of y for all y belong to that particular neighborhood. Okay, but for any arbitrary y means for any of the y. Let's say what if I get a y here, then the function value here will be less than the function value at x star, right? So for every arbitrary y, I can write like this, na? uh, fx star is greater than f of y, correct? Do you understand this step?
Yes.
Yes.
Okay,
Yes.
so for any arbitrary y, the fx star should be greater than f of y, okay, for any of the y. Now, what you see, what you do, okay, so we name it as equation 1 and we name it as equation 2. And I say plug equation 2 in 1. So what was equation 1? Let's write equation 1. Let's say alpha x star plus 1 minus alpha y should be less than equal to alpha fx star plus 1 minus alpha fy, and x star and y, they belong to the domain of f, right? So I know this equation, okay? I rewrite it form of x star and y. Now I simply put 2 in this equation. So what happens when I put 2 in this equation? So it's basically f of y is less than f of x star. Okay, so I will be replacing f of y. See, there is an inequality sign here, so I can replace f of y with f of x star here, right? Using 2, because in 2 f of y is less than f of x star. So okay, so it basically says that oh, just a minute. I think I flipped the inequalities. Just a minute, let me see the proof.
So here x and y are any 2 points on the convex function, right?
Yes, yes. Just yeah, there are any 2 points. X. Just a minute. What I did. Just flip the inequality. Function value is greater than or equal to this any point, which should be the other side, right? Uh, mm, okay, I think I messed up in a proof. Okay, let's leave. I won't say leave, but let me come back to this proof at the end of lecture. Okay, let me come back to this proof at the end of lecture.
Yeah, I think you need to take x star, you need to apply this equation twice. Once between x and x star and once between x star and y.
Um, X star and Y. So an X and X star, if I apply, no. I okay. Let me just get back again to this proof. Okay, by the end of the lecture. Okay. Anyway. Mm, Another good, what you say, proof would be, yes. Can you please mute? There's a lot of noise. Excuse me, your mic is on. So can if you yeah. Yeah. So another good proof can be, so it's basically it's a statement. The statement says that if f is convex, then its gradients are non-decreasing. Okay. So if I give you so its gradients are non-decreasing, it means if f is a convex function, okay, and there are 2 points z and x that belongs to the domain of f, okay, and z is greater than x, then it means the gradient at z will also be greater than the gradient at x. Okay, so this is the meaning of this statement. If you take any 2 point, if the function value at one point is greater than the another one, then the gradient value at that point will also be greater than the another one. So it's basically a simple proof. Okay. Have you heard about MVT or mean value theorem? Hmm?
Yes.
So
No.
okay, I will tell you the MVT. Okay. Can you please mute yourself? Like there is a noise going on behind. Okay. So MBT says that if I have an interval, okay, let's say I have this closed interval x comma y, and there is a point that belongs to this interval such that z is greater than or equal to x. Okay, then MVT says that the gradient at the point z, okay, it's basically equal to this slope value, or let me tell you geometrically. So this is what MVT says. MVT says that, okay, so let's say that you have a function over here, okay, and these are point x and y, okay, and let's say there exists a point And okay, so these are 2 points x and y. Okay, so MVT says that if I draw a line here, what will be the slope of the line? The slope of the line will be fy minus fx y minus x, right? So MVT says if fx is a if f is a convex function, you choose 2 points x and y and you join them with a line, then between these 2 points x and y there exists a point z. Okay, it proves that there exists a point z somewhere in between, such that the gradient at the point z, the gradient, okay, the gradient at the point z will be parallel to this line, right? MVT says if you have any 2 points and you join a line, you will get a slope. Now, between these particular 2 points, there exists a point z such that when you compute the gradient, so gradient is nothing but slope, the gradient will be parallel to that slope. Okay, so this is what the MVT says, mean value theorem. Okay, now it's clear.
Yes, Alok.
Okay, so now what I was saying, so we have to prove that if fx convex, then gradients are non-decreasing. Okay, so as I said, let f be a convex function and let z belong to closed interval of x comma y, where z should be greater than or equal to x. Okay, now using MVT, using mean value theorem, I can write this. Fine. I can say that I choose a z such that the gradient of the z is equal to that of the slope. Okay, let me choose a z such that the gradient of z is equal to the slope. Okay. Now, I know that f is convex. Fine. So this will be my statement number 1 and this will be my statement number 2. From convexity of f, I know that f is convex. Okay. So when you say f is convex, I can always write as this. This is the earlier property that I introduced in the starting of this lecture and at the end of the previous lecture, right? If f is convex, then I can write it like this, right? Now I can rearrange the terms. Now, what is this thing from the equation 1? This thing is nothing but f dash of z, right? So hence prove that the gradients are non-decreasing. We claim that z is greater than or equal to x, and we prove that f dash of z will be also greater than or equal to f of x. Hence, for convex functions, the gradients are always non-decreasing. You got this proof or you have any doubt? Hello?
Yeah, it's okay, sir.
It's okay, right? For others also it's
Fine.
okay? Yeah. Okay.
Yes, sir.
So,
Yes, Alok.
okay, so let's move forward. Let's, okay, just try to find good. Uh, mm, okay, what other proof we can show? Yeah, there is another very, very important proof. There is another very, very important statement. The statement is if
One doubt, one doubt.
yeah
How does
yeah
this statement get generalized to multi dimensions?
You can just put a gradient here, na?
So does it mean that if I have two variables, del f
Hmm.
by del x and del f by del y, both will be greater than?
Okay, sorry, in multidimensional case, you have to take this. Okay, so your multidimensional case, your gradient of the x, it will be like this, right? Dx1 dot dot dxn, right?
Yeah.
And so it's basically you have to take a norm of your gradient.
Okay.
Okay, so and in a multidimensional case also you cannot just directly write that x is less than z because these are multidimensional variable then, right? x1 to xn or z1 to zn, I think. So you have to always take some norm of the measure and you can write with respect to the norm. However, I am not very clear about the multidimensional case because that's not exactly being taught. But the thing is, yes, it does happens in multidimensional also. Okay, it does happens in multidimensional also. The gradients are non-decreasing. Okay, so the next statement it's a very important one. So if f is convex, then Hessian of f HF is positive semi-definite matrix. Now tell me how many of you know about Hessian and positive semi-definite.
Hessian is double derivative, right?
In high dimensional it's double derivative. So shall I teach what is Hessian like for the sake of everyone? Okay, don't know. Okay, then I will explain. Okay. So okay, if I have a function f that goes from Rn to R, okay. So it means basically f takes input which is high dimensional. So x here is a vector. Okay, let's say it's an n dimensional vector x1 to xn. Okay, so so the gradient, first thing, the derivative of the f, okay, at point x, grade of, this is known as the gradient, it will be partial derivative of this dx1 dot dot df by dxn. Okay, we call it gradient. Now how can you compute the double derivative? So the double derivative is denoted like this, or it is directly denoted by h of x, hf of x, and it's basically a matrix. And the matrix is this dx1.
The first one should be del square f
Yeah,
by del
double,
x.
double, 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 yeah. Okay, so the Hessian is basically this matrix. Okay, so you guys know what is this thing, or shall I explain this also? Like it's totally fine if you don't know. I can explain these elements also. Okay, just type in the chat box if anybody doesn't know. So I will go ahead and explain. Okay, no one. Okay, there is a message. Okay, explain. Fine. So let's say I have a function of two variable. Okay, x1 square plus x2 square. Now if I want to compute df by dx1 dx2, so it will be, first I have to compute with respect to x2. Okay, treating x1 as constant. First, I have to compute with respect to x2, treating x1 as constant. Okay, so that will be 2x2 plus 2x1. And then, so, and then I have to compute with respect to x1. So it will be by treating x2 as constant. So it will be 2. Yeah. You got it? So when you have these elements like dx1 by dx2, what you do, take the function, first compute your gradient with respect to x2 or the innermost. Okay, whatever the result you get, then compute the, yeah, okay, yeah, fine. Okay, so this is a matrix. Okay, now I think we are clear about the Hessian. So this is known as Hessian, okay? So you guys know about positive semi-definiteness of matrix, PSD, what is known as PSD? You guys know? What is a positive semi-definite matrix? Okay, so a matrix A, okay, is called positive semi-definite. So let's say this matrix is n cross n matrix. So it's called positive semi-definite if x transpose ax is greater than or equal to 0 for all x in n-dimensional space. Okay, this is the basic definition of positive semi-definiteness, that a matrix is said to be positive semi-definite n cross n if I can take any n cross n vector and do this particular math. I will always end up getting some value which is equal to or greater than 0. Okay, for any of the vector in n-dimensional space. So this is known as positive semi-definiteness. And it has some nice properties that their eigenvalues are always greater than or equal to 0 and all. Okay, so this is known as PSD. Fine. Okay, then, yeah, to prove, okay, so let's get back to the proof. To prove that if f is convex, then HF is PSD. So if f is a high dimensional convex function, then it's Hessian at any point. Okay, at any point? No, 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 not at any point. Sorry. Okay, so it's basically it's Hessian. Yeah, it's Hessian at any point. It will be positive semi-definite. Yeah, it's Hessian at any point. It will be positive semi-definite. Okay. Now, okay. So, hmm, okay, just a minute. How can we proceed to the proof? Okay, so the proof is not very simple. It's a bit tricky proof. Okay, now what is given with us? We are only given with f is a convex function. We are only given with this information. Okay, and f takes x as input, which is basically a high dimensional vector, right? And gives a scalar value. So that's why I write this as r raised to n to r. It's a mapping between n-dimensional space to real line f. Now there exists something, I can write g of t. Okay, g of t is equal to f of x plus tv. Okay, I define a function g of t, which is nothing but fx plus tv. Okay, and t here, it's basically a scalar, and x comma v, they are vectors. Okay, So I define a function g of t, which is equal to f of x plus tv. Okay. And I claim that g of t is also convex. And it is convex. Okay. If you have any convex function f and you define a new function g of t such that f of x plus tv equal to g of t, then g of t is also convex. We won't go into the proof because this proof is not important to us for machine learning. So we'll skip the proof. But for any convex function f, if I define a function f of x plus tv where t is a scalar value or the real number as g of t, then g of t is also a convex function. Okay, so let's remember it as number one. Fine. Now we say that g of t is convex. It means from the earlier proof that g dash of t2 will be greater than equal to g dash of t1 for all t2 greater than equal to t1, right? Non-decreasing property, right? So it's a non-decreasing gradient property of convex function. Okay. Now g dash of t2 is greater than equal to g dash of t1 for all t2 greater than t1. So what it says that non-decreasing gradient property, it says that my gradient g dash of t is non-decreasing. Okay. Non-decreasing, it means if I take the double derivative, it will also be greater than equal to 0. That's what the non-decreasing property in other sense it tells you. Okay. Now, okay, now the thing is g of t is equal to f of x plus tv. Now, can anyone tell me how can I write g dash of t? What can be the g dash of t where x and v are vector and t is a scalar? So have you guys know about the chain rule, right? Or differentiation?
Yes.
Okay. So if I'm taking the derivative with respect to t here, I am supposed to take the derivative with respect to t here also, right? And according to the chain rule, I will first differentiate this function f, okay? So let's say I differentiated, it is f dash of x plus tv, fine? And now I will differentiate this particular term here with respect to t. What I will get? X will be constant, t will vanish,
V.
and I will be left with v on. So it will be basically v transpose. Because v is a vector, you have to write it like this. Okay. So g dash of t is nothing but v transpose f dash of x plus tv. V transpose is a vector and f dash, the gradient of f, it's also a vector, right? Gradient of f is a vector. So basically, it's a dot product. It's a dot product between v and gradient of f. And the dot product is scalar. Correct? So the derivative of g dash of t can be written as like this. So this is no, this you can write like this, okay? So any point x comma y can be written as x transpose y. This symbol denotes this. Okay? Tag it as number 3. Now double differentiate g. Okay. From here, if I again differentiate it, so v transpose will be constant and I have to take double derivative of, I have to take another derivative of f dash. Okay. So it will be, now again, I have to differentiate inside term. So I will get a v over here. You got it? Does anybody has any doubt?
No.
Okay. So g double dash of t, it can be written as V transpose or h of f v, because the double derivative of any vector function is denoted by h, Hessian, right? And we already said that due to the non-decreasing gradient property, the double derivative of the convex function will always be greater than or equal to 0. Okay, no, Bhavya is saying no. No means you're not able to understand? Like which part, can you elaborate? Okay, you don't have any doubt. Fine. Okay. Yeah. So using the non-decreasing property of convex functions, their double derivative is always greater than or equal to 0, and hence V transpose HFV will always be greater than or equal to 0, which implies HF, which is nothing but the double derivative of the function f, is positive semi-definite matrix. Okay. So these were the three main important proofs related to convex function. Let's note them down. Number
Hello,
one.
one
Yeah.
question. The
Yeah.
function gt is
Hmm.
is the it's like that we are moving the uh, domain of values of x by tv.
Yeah, exactly,
Uh,
exactly.
so the behavior of gt is similar to the fx, right?
Yeah, yeah. Yes, yes. That's why if f is convex, gt is bound to be convex.
Okay.
Okay, that's a good observation. That's what we are doing there. So what we learned from these three things, that for convex function, three main properties, that every local minima is a global minima. Gradients are non-decreasing. Third thing, it's Hessian. Hessian of convex function is PSD always. These three are the main properties that we are going to use in machine learning or deep learning very rigorously. Okay.
Is there any physical significance when the Hessian is exactly zero?
Hessian is exactly zero. It means your double derivative is exactly zero. And when your double derivative is exactly zero, it means that particular point is an inflection point, right?
Inflection. Okay.
Yeah.
Okay.
So something like this, if you have a function like this, then here your double derivative is bound to be zero, right? But if you have a function like this, then your double derivative will be a positive one. But these are known as valleys. Yeah, these are known as valleys. Okay, so in loss functions, you can encounter these points also where your gradient descent method will get stuck forever. It won't move upward. Okay,
So
so that's
geometrically
where
also
the
we can understand. Geometrically also we can understand that the double derivative is always greater than or equal to zero.
yeah. So double derivative is always greater than or equal to zero exactly. So that's the PSD of Hessian. Okay, I think we are done with the calculus part, whatever the prerequisite we had. So we what we discussed so far. So far we learned about sets, bounded sets, closed set, open set, convex set, convex function. Okay. So far we learned about these things, right?
We also discussed about limit point, interior points.
Yeah, these are like closed set and open set. They come within that. Because that's the definition we required to define a closed set and open set, and how to compute minima when your set is open. And we also discussed something about supremum and infimum. I will share you the lecture to latex as soon as possible so that you can have a revision. And from lecture 3, I won't be sharing latex because this lecture is being already recorded. Okay. So I will share you the recording link. Okay. So, yeah, so far so good. These are the basic tools that are required to understand machine learning from calculus point of view. Okay. Now we will start. Actually, we will quickly start something, another prerequisite, number two, that is the probability. So tell me, how many of you have grip on probability? Like, do you understand the terms probability density function, probability mass function, uh, expectation, conditional distribution, joint distribution, conditional expectation? Just quickly tell if you have been through a basic probability course or not.
Not much.
Okay, okay, cool. Then we will start today. Okay. So, okay, then we will have a quick discussion about all these terms. Okay. So let's start with something known as probability density function, or what you know as PDF. Okay. So, um, yeah, a function. Okay, do you guys know what is a random variable? Okay, let me define random variable first. Okay, so a variable x, capital X, which is a mapping from your sample space to a real line. Okay, it's basically known as a random variable. Okay, so random variable is something that takes some elements from your sample space and maps it to a real line. So basically, let's say that I am um, rolling a die. Let's say I'm rolling a die. What will be its sample space?
One to
Okay,
six.
let's say. Okay, yeah, let's say it will be a confusing problem, but let's take another example. Okay, because in sample space you will have a numerical value and real line you also have numerical value. So let's see. Let's do an experiment where we are tossing a coin twice. So what will be the sample space? It will be this, right? Tossing a coin
Yes.
twice. So if I define a random variable x, okay, let's define the random variable as uh, number of heads. We are defining this random variable on this sample space, and I define the random variable as number of heads. Okay. Um, so just quickly tell me what are the possible values this random variable can take.
0, 1, 2.
Exactly. Right? So there was a sample space where these elements were there. Fine. Now you are using the x to map them on a real line, right? In real line, I have 0, I have 1, I have 2. So 0, it means this particular point is being mapped to 0 via x. These 2 points are being mapped to 1 with x, and this particular point is being mapped to 2 with x. So a random variable x is basically, when you define a random variable, it's basically a mapping from sample space to a real line. Okay, this is known as a random variable. Now we come to PDF. PDF is probability density function. Okay. Yeah, probability density function. Okay, so before coming to that also, okay, yeah. The random variables, okay, the random variables can be of two type. They can be continuous and they can be discrete. In this example, we can clearly see the random variable can take discrete values, right? So x here is a discrete random variable or known as DRV. Okay. Now this is an example of discrete random variable. Now I will give you an example of continuous random variable. Okay, continuous random variable, it's basically you can think
Temperature
yeah.
reading per day.
Yeah, exactly. Temperature reading. Because at any particular time instant, the temperature is basically a continuous function, right? It can take any value. Okay. Like it can take 25.6, 25.69, 25.67, dot. It can take any value. But discrete random variables, they are supposed to take only discretized levels. Okay, so it can be 1, 2, 3, 60, 50, 100. So they are only discrete things. Okay, but continuous random variable, they can take any value, 1.1, 1.2, 1.11119, and so on. So it's basically the continuous random variable, they are defined on an interval, while discrete random variables, they're defined over a set. Okay, or you can imagine this thing like, let's say I have two scale with me. Okay, let's say scale s1 and scale s2, and you are measuring height of person, where scale s1 will give you only integer values. Okay, so the height can be, it can give you 60, like it can give you 6 feet, 5 feet, 4 feet, 3 feet, 7 feet, right? But s2 s2 has more precision. Okay, but here the s2, it is more precise. More precise, it means the S2 will give you a more precise length, like 6.1 feet, 6.2 feet, 6.3 feet. Okay, so these two are scales where it will give you approximate value S1, and S2 will give you highly precise value. Okay, so here S2 is basically continuous random variable and S1 is basically discrete random variable. So continuous random variable is nothing but something known as it is very precise in nature. Okay, while discrete ones are not. So do you get the concept of continuous random variable and discrete random variable? Guys?
Yes, sir.
Yeah, cool. Okay, so now we will define something. Let me define something known as, yeah, now we can actually define PDF or the probability density function. So for a random variable x, for a random variable x, a function which is written as f subscript capital X and x is probability density function if it satisfies two property, that fx will be greater than equal to 0 for all x belongs to x. X means here your random variable is basically an interval, right? It's an interval. So whatever value you pick in that particular interval, your density function will be greater than equal to 0. And secondly, if you integrate it throughout the interval, it should give you a value of 1. Okay, so any function if satisfies these two values, they are known as probability density function, PDF. Okay, of a random variable x, PDF of x. Actually, PDF is alone, PDF doesn't make any sense. You have to say PDF of x with respect to a random variable, you have to say. Okay, now similarly, as we are doing integration and these things here, so this particular x, so the PDF probability density function of any random variable x, it's only defined for continuous random variable, right? For discrete random variable, you have something known as probability mass function. So your so you have a random variable x which takes some values x1 to xn, and p of x is a probability mass function if p of xi is greater than equal to 0 for all xi in x, and second, the integration will become summation, right?
1.
Yes.
Yeah, equal to 1. Okay, so for discrete random variable, we have PMF. For continuous random variable, we have PDF. Now, if you can visualize, a continuous random variable looks something like this. The PDF of a continuous random variable. It's basically a graph where the area under it should sum off to 1. Okay. Can you tell me, can this be a PDF? This graph? Is
No,
it a
sir.
valid PDF?
No,
Yeah.
sir.
Why?
Because the area will get cancelled out, the crust and the trough.
Yeah, that's the second point. But using first point, you can also say it cannot be a PDF. Why? Because this thing, see, the function is taking negative values.
Negative value.
Probability cannot be negative, right? PDF is nothing but probability. It says that at this particular point you have some, okay, it doesn't say, but PDF is basically like you define a particular interval and you say that within this interval you have, when you compute the shaded area, you have this particular probability, right? So here you are getting something in negative, right? And probability cannot be in negative. So using the first comment, you can also discard, but whatever you said is also correct. The area will get cancelled out and it will be 0. But using the first thing, you can say that the function cannot take negative values. Okay. And yeah, so we will quickly define some properties. Property number 1. So if fx is a PDF, okay, for continuous random variable, okay, let me define you one good thing. If you say that, let me compute a probability between these 2 points a and b. Okay, what is the probability that the continuous random variable x lies within these 2 points? Okay, so let's say I have this continuous random variable and this is the PDF and these are points a comma b. So whenever you are defining probability, the probability is basically nothing but the area. Okay, when I say compute the probability between this particular points a and b, you just have to compute the area of your PDF between these 2 points a and b. Okay, so the area corresponds to probability. Okay, and how do you compute the area? Using this, right? Yeah, integrated. Okay, so this is how you compute probability. Now, can anyone tell me, for a continuous random variable, what will be the this thing at a particular point? Let's say I want to, okay, we have talked about the interval, like area of the interval computes the probability within an interval, but what about a single point? What will be its probability?
You have to take the probability within a small delta around that point.
Yeah, small delta, it means we are again talking about an interval. So what you are talking, you are saying that like this. So this is nothing but integration, no?
Yes.
Okay. But I am saying at a single point, what can be the probability?
Single point.
Okay. Um, the probability will be zero. For continuous random variable at a single point, it will be zero. Reason. Okay, let's get to the reason. The random variable x, it can take how many values? It can take
Infinite.
infinite number of values in an interval, right? So if I say that x is defined on an interval a comma b, it can take infinite number of values. Now if I say you what is the probability of a value of a point x inside the interval, so what is the basic notion of probability? What is the basic notion of probability? It's basically the success by number of trials, right? So it's basically the success of one point divided by how many number of trials you have. You have infinitely many number of trials. That makes it zero. You got my point?
Yes, sir.
Okay. See, for a discrete random variable 1 comma 0 1 2, what is the probability of 1? It's basically 1 by 3, right? But for a continuous random variable, let's say 0 to 1, what will be the probability of 0.5? It will be 0 because we have infinite number of points between 0 to 1. Okay. Everything clear so far?
Yes.
Now we define something known as expectation. That is also known as mean of random variable. Or before going to that, let's define some probability models. And within that model only, we will define this expectation and variance things. Okay, so we will talk about some famous probability models. So it will have continuous models, it will have discrete models. I will explain everything. Okay, so these are basic models that you should know before proceeding to machine learning because they are widely used there. Okay, and okay, so let's start today's lecture. Let's start this topic by continuous models with continuous models. Okay, so the
What is
first
number five? What is the number five?
multi-Nolly, like Bernoulli, there is something known as multi-Nolly also.
Oh, okay.
So for continuous model, the first model is Gaussian model. So for every model, we will define few things. We will define a probability density function or probability mass function. We will define its expectation. We will define its variance. Okay. So for Gaussian model, um, we can say X is a Gaussian random variable. X is a Gaussian random variable, and the PDF or the Gaussian model f of x is defined as like this. EXP is the exponential, and this is the power to the e. Okay, so the PDF of a Gaussian distribution is mathematically it's defined like this, and I will explain about the parameters. So it looks like this. Okay, so the graph is basically like this. So the parameter mu you are seeing here, it's basically x equal to mu. Okay, and this peak is attained at 1 by sigma root 2 pi. So this is how the PDF of a Gaussian random variable looks, probability density function. Okay, and here mu is nothing but mean of random variable x, and sigma square is variance of random variable x. Okay, so let me tell you one thing, that the mean, okay, mean is basically defined as this thing, e of x, or it can be read as expectation of random variable x. Okay, so it actually it's defined like this. Like we can say mean is nothing but expectation or weighted mean. Expectation is more of a weighted mean. Okay, so it's defined as it's basically defined as expectation over the random variable x, and with a PDF x with a PDF fx. This is how you can write an expectation. Okay, and it is basically denoted as integral minus infinity to plus infinity x times of fx dx. Okay, now if you just plug the Gaussian density formula here, if you just plug the formula here and you solve the integral, it will be a very lengthy integral. You will get the expectation is nothing but the mu. Okay, so the mean of a Gaussian random variable is mu, and mean can also be like thought of as, if I have this particular density function, so mean will be a point such that the density function is balanced, or balance means like center of mass. The mean is nothing but the center of mass of a density function. If you just like draw this thing in a cardboard, cut it down, so the center of mass will be its mean. Okay, so mean is tagged as a center of mass sometimes, like for the quick analogy. Okay, and now we have variance. Okay, so for mean it's clear, right? You got what is mean of a random variable.
Yes.
Okay, the variance is basically it's defined as spread of a random variable. So let me quickly tell you, okay, if I have this density function, okay, it's a random variable x1, and if I have this random variable x2, so which one has more spread in it?
X2.
H2.
Exactly. So the variance of x2 will be always greater than variance of x1. So variance, it can be termed as uncertainty also, right? More the variance, more is the spread. So if you have more spread in your information, it means your information is more uncertain, right? But if you have less number of spread, it means you are sure about this. Okay. So variance is defined as expectation of x minus mu whole square. Mu means mean. So for any general random variable, it is defined as like this: x minus expectation of x whole square. Okay. Yeah, and you understood that this expectation is a real number, right? Because when you perform the integration, it will be a real value. And so does the variance, okay? So it's a real number, so it can be written as integral minus 0 plus infinity x times of, sorry, it will be written as x minus expectation of x whole square f of x dx. This is how you can write. And this is known as variance, denoted by basically sigma square. Okay. Now, if you open this, okay, before opening, let me just write down a quick thing we won't derive. So the variance of a random variable can be defined as x minus e of x whole square, and which can further be written as e of x square minus expectation of x whole square. So this is the formula for variance, okay? You can either write like this, compute like this, or you can directly do this. So for any expectation of a random variable e raised to xn, it can be written as like this: x raised to n, the density function dx. Or if you have any function of a random variable also, okay, let's say f is a function of a random variable, the expectation will be like this: let it be g. Okay, so expectation is basically an operator which can be written like this. So this is the formula of variance. Fine. So far, any doubt?
No.
Okay.
What
So
is
for
the
Gaussian,
second? What is the
what?
significance of this?
Very.
No, the second equation. I am not able to.
This
The d of
equation.
x. Yeah.
So it's
This is
basically
d
if
of
I,
x.
yeah. So it's basically if I have a random variable x, okay, I apply some function on that g. So I will get a random variable g of x. Okay. So whenever you apply a function on a random variable, the output, the resulting thing, it may or may not be a random variable. Okay. It may or may not be a random variable. So let's say that I have a random variable of success of heads in 2 tosses. I define another random variable 2x. Let's say g of x is equal to 2x. So it will be like this, right?
Okay.
Right. So now basically I am saying that, okay, I don't want to compute the expectation of x, but I want to compute the expectation of g of x. Okay. So expectation is a particular operator, okay? So if I want to compute the expectation of a random variable g of x, I will just write g of x and the PDF of x.
Okay.
So it's basically computing expectation of a function of a random variable, okay? So it's basically g is a function of a random variable, and which may or may not be a random variable. Basically gx can be a random variable, it cannot be a random variable. So it has to satisfy some properties, but that will be a probability course. I don't want to go down there. Okay, so for Gaussian, random variable, we have PDF, we have PDF, we have mean defined as expectation of x, which is nothing but mu, and we have variance, which is defined as expectation of x minus mu whole square, which is nothing but sigma square. Okay, so these are the, and this particular tuple, the mean and sigma square, these are known as parameters. Okay, parameters, it means it defines the distribution, right? If I say define a Gaussian distribution, you will say that it's basically it has a mean mu and variance of this, or you can say it has mean 0 or variance of some numerical number. So whenever you specify a Gaussian distribution, you specify them using mean and variance. Okay, so basically they control the shape of the distribution. If the variance is high, the Gaussian will be like this. If variance is low, Gaussian will be like this. Fine. And mean, basically it shifts the curve. It will take this and shift anywhere. So the variance controls the spread while mean controls the shift. Okay.
What are the typical distributions that follows a Gaussian model? I mean, is there any standard examples?
Yeah, so almost every real life phenomena they follow the Gaussian thing. Okay, like yeah, almost every real life phenomena. So see, the basically it's like, okay, if I want to define it to you mathematically, I suggest you to look something in the internet known as CLT, central limit theorem.
Okay.
Okay, central limit theorem. So central limit theorem says that when you have number of random phenomena occurring, okay, so let's say x1 is a random phenomena, x2, xn is a random phenomena occurring within some environment, okay, within a some closed space or some environment. Now, if you observe all these particular phenomena, okay, at once, that particular thing will follow a Gaussian distribution. Let's say that I am observing, I have a jar and I have some gas molecules with me. Let's say I have 10 number of gas molecules. It's just for the example, you cannot compute the number of gas molecules, by the way. So I am observing the, let's say, temperature of the gaseous molecules, okay, all the 10. I am some plotting some curve. And let's say time t equal to 9:50 p.m. I'm supposed to watch their average temperature. So I will be adding all the temperatures, and this particular thing will be following a Gaussian distribution. So Gaussian distribution, it you can like easily see it in nature. Okay, like any random phenomena or any, what you say, average of random phenomena or any summation or a combined random phenomena, they are always represented by Gaussian. And if you read the CLT, the central limit theorem, you will get a good thing about this, because it will say that if I have some n number of random variables, x1 to xn, these are n number of independent random variables. Okay, they are known as IID, basically independent and identical random variables. So if x1 to xn follow any distribution, if they follow any identical distribution like x1 to xn, it they all should be independent with each other, and they all can follow Poisson distribution, Bernoulli distribution, or anything. So if they are, as far as they are IID, they are independent and identical. If you keep on adding these things and take their average, then the summation of the random variable, it will be a Gaussian one. It's a very vague statement. Mathematically, it. Okay, I suggest you to read this, because I vaguely, only vaguely, I can say the sum will be Gaussian one, but mathematically, when you read it, you will get a more maturity. It won't be 100% Gaussian, by the way. Okay, there will be some property of this summation of random variable that will behave like Gaussian. Okay, there will be certain properties that will behave like Gaussian and certain properties that won't be behaving like Gaussian. Okay, but for sure there will be certain properties that will be Gaussian in nature.
But
So
generally, you can say that as the number of experiments you keep adding and infinitely many experiments you do, then it tends to follow the Gaussian.
it doesn't exactly tends to follow the Gaussian. It's cumulative density function. the cumulative density function behaves like a cumulative density function of Gaussian. Okay, it
Okay.
doesn't tells that the sum is a Gaussian thing. I will define what is a cumulative density function in next lecture. Maybe we are out of time now, so I will define what is a CDF. Okay, that's why I was saying that if this summation, certain property of this summation behaves like Gaussian, like certain properties like the cumulative density function. The CDF of this distribution will be Gaussian, but I cannot guarantee about the PDF of this distribution. Okay, I don't know whether it will be a Gaussian or not.
Okay.
Okay, so I suggest you go and read CLT, central limit theorem. Okay, it will give you a good overview, like how the things happen in nature. Okay, so I think we will stop for today, and in next lecture I will be defining joint distribution, and I will be defining Bayes rule. Okay, that Bayes rule covers everything: joint distribution, conditional distribution, and everything. And I think next lecture the prerequisite part will be end, and we will jump to the machine learning from next week. We will start with basic classification problem, and then we will try to dig deeper. Okay, so
Okay, Alok.
okay, just oops, where is the meeting?
Yeah, are
Yeah,
you
okay.
sharing the recording of this?
Yeah, I am sharing the recording, definitely. Okay, so just let me know how to stop the recording. Okay, stop recording. You want to stop.